I mean, I can also send a updated Excel file, and so it's easier for you, maybe.
Oh, I have the Excel file. Let me see. Yeah, the last name here is Manish.
Yeah, let me check.
16 names I have here.
How many?
16.
Okay, let me quickly check.
Oh, 15. One is there's a space.
Yeah, that might be correct. Yes. Okay. So if you can share it, I can distribute.
Yeah, I'll send you back the
Okay, cool.
The Excel file.
Okay. Very good. So let's start with the workshop for today.
Okay, so we want to show how to make the analysis and the stresses.
Exactly, and thanks again for sharing and joining in. And this will be the last of the 4 sessions that we organized. So this will be at the same time kind of the closing ceremony of this workshop. So yeah. The floor is yours, Jerry. Thank you.
Thank you. Thank you. Let me find. So share screen. Everybody sees my screen?
Yeah, it's visible.
That's fine. Okay, so today we will show again how to run the analysis part and post-process the data. So first of all, let's load. I think this one we did. No, that was made with another version. I have so many versions, I get lost sometimes. No, this one. Okay, let's do it from very fast. I will do a new one from scratch because I don't really. I think I've used a new version last time, so the file I cannot open the file right now. But this is a good exercise. I will go very fast on doing an IPAR with polls, so we can have a look at all the process from the beginning. Remember that I will do a copy paste to go fast, but no, I would use Grasshopper so everybody can do it. Clearly, I will draw to go fast. I will not do a parametric model because everybody knows that doing a parametric model is quite time consuming. So I will just draw my poles, 4 meters, and I will copy these poles here and here. Then I will do a circle, 5 meters, too big, 3 meters. And let's go to the layers and poles. These 2 elements go into the poles. Then let's make into the layers, I will make cables. Activate the cables and draw 2 stay cables here. I will make a mirror, so we have a symmetric model this time. And then I get these 2 and I mirror them. Okay, and we have the cables, and then here I put my boundary, and I draw the boundary edges here. Explode them. And let's make also the links. And I'll make here 0.5 meter link. I get this one and I mirror it again. So I have made perfectly symmetric boundary. Let's make the last one, that's a surface. And I will make a surface between 4 edges, edge curves. Okay, so this is my, so basically I have generated this. Clearly, it's not tensile, it's an Earth surface, but we are quite near. To speed up my grasshopper definition, I will make the ground points. Take off the grid snap. So I'm showing you another way how to do all this. So I have made another one here. Now I'm going to use Grasshopper, and basically we have generated all the elements that we need. So we can easily generate the model. Let me see if Grasshopper is working. Okay. Now, if I go to Xcube, let me see if it's connected. Get seeds. Okay, it's working. Fine. The nice thing, I don't know how many of you know Grasshopper, but there are many plugins available on Food for Rhino. And one very interesting one is Elephant. So if you are a Grasshopper user or you're going to use Grasshopper, I highly suggest to download this Elephant plugin. Many tools, we're not going to look at the tools, but there's one interesting one that is reference by layer. Reference by layer will just load the data in a layer from Rhino. So what we need now is the layer. I think we have here a list of layers somewhere. I don't find it. It doesn't matter. We will use the layer names. So I just click here, and the first layer that we want to reference is the poles. So I click here, poles. We plug it, and we see that we get here reference line curve. So we have got the geometry from the pole layer. And this will be my first input for generating the poles. I will copy paste. The second layer that we want to reference is the cables. And here again, we see that we have 4 curves. Then we have the links. Okay, 2 curves. Then we have the points. I need to change these points. Let's make a new layer and call it points. Select these points here on the ground. and put them on the points. Okay. Points. Five points. Something is missing. These here.
The boundary is missing.
The boundary is missing, but I think I don't need it because I have we have 6, 8 points. Okay, 8 points. And then I don't need the boundary because I have made the surface. So we can skip the boundary and the surface here. Surface. Okay, so we have referenced through these through at the front. We have got all the geometry that we need. The first step clearly is making our tensile mesh here. Because we have a surface, we need to mesh it. We go into the mesh parameters and we will find here mesh BREP, because the surface is a BREP, it's a geometrical definition. So the mesh BREP wants a BREP as an input and generates a mesh as an output. Now, we see here how big the mesh is. Clearly, we can change the settings here. And in the mesh parameters, we have different kind of settings for the quality. For example, I can get quality settings, I input, but you don't see much better meshes. Ixcube has a nice tool. If you go into the Ixcube tool, has a remesher. The remesher is a FEM remesher. The nice thing about this mesh tool here, that it will generate the final element mesh. You know the difference between a normal mesh and the final element mesh. Generally, when we use triangular elements, we want them to be we want them to be more or less equilateral. Triangles made by 4 edges with the same size. This is always a good way to go when we're running a structural analysis or FEM analysis over meshes. So large and skinny meshes are to avoid because they make bad numbers at the end. Mesh parameters, the size of the model is 10 meters by 10 meters. So I will make a mesh 0.5 by 0.5, half a meter. And then we input the mesh and we get this mesh here. That's it. One good thing that you can hide using this tool here, you can hide different elements of Grasshopper, so we see only those that we want to show. What is missing here is the edges of this mesh. Now, remember that the edges of the mesh is not just the line that have drawn from this point to this point, but it's a kind of polyline. I need all these small pieces. I need a line that is split at these points. Only with a line splitting these points, that has these points, will get merged to the mesh. A single line from here to here will not be merged on the mesh. So clearly what I need is the boundary of this mesh. So how can we do that? Well, luckily we have tools to detect the boundary. There are so many tools inside Grasshopper to detect the boundary, but there is one that you can also download. Let me see if I have it here. I don't have it. Okay, I don't have it, so I have to go by. Doesn't matter. Let's do it like this. We can go into the mesh tools, and mesh edges is one of the tools. If I input the mesh edges will give us a list of edges. Now, we have naked edges, integer edges, and non-manifold edges. Clearly, we want the naked edges. If I use a curve tool and I plug into the naked edges, we can see now that we have detected all the edges of our mesh, the green lines. Now there's one step missing here because I would like to join these meshes based on the angle. I would like to have only 4 of these edges. And to do this, this is a bit tricky. I have an option here. Let me see if I have Cube Tools. I don't have it here. Let's see, in Kangaroo, there is a tool. Mesh. Mesh corners. No, there's no tool. It doesn't matter. I will go to be fast. I will go ahead, but clearly, one step should be to join these edges based on the angle between each of them and make 2 4 lines. This tool is available in Rhino Membrane. There is a tool to do that, but it doesn't matter. We'll do it later. Clearly, now in this moment, I don't have the right tool, and since it will make time to do it, I want to avoid losing time for doing this this task here. It doesn't really matter. Nothing will change about the solution, so we can skip this step and go to the next step. These are my edges. So now we have all the pieces that we need. We have the edges of the mesh. We have the mesh, the poles, the cables, and the ground points. So we can start generating the model. We go into the Ixcube. The first thing that we want to do is to create a mesh set. Another tool that I use quite often, and I suggest to use it, is the telepathy. Telepathy is this tool that basically we can send data from one part to the other of the canvas, Grasshopper canvas, and it avoids making a huge messy definition. So we can be quite, we can keep everything nice and ordered. So this is my mesh set. This is my mesh. We need to input the pre-stress. And first of all, we need to define the warp and the weft direction. So I will draw a line just to have. I will go into the library, into the. We have to be careful now because we are referencing the layers. Anything you draw on those layers will be read back by these reference objects. So you have to be careful. And what I need is a plane. So I go into vector, plane, construct plane. The origin is this one here. The x-axis. Clearly, and the epsilon axis is this one here. Okay, so this plane, I have defined the plane that cuts the surface at 45 degrees. And this will be my warp weft plane. Here it is. So we define, with this plane, we define the warp direction. Then we want to define the pre-stress. And we define the warp and the weft pre-stress. The seed, where do we get the seed? Well, we have got the seed here. If I input a panel into the seed, here we have all the seeds. And we can reference one of these with the listed item. So I want to reference the membrane is seed number 6. So I input 6 here. And then using telepathy, we input it to the telepathy and get the seed element down here. So this one here, I would group it, Control G to group it. And this is my membrane. Okay, so this is my membrane. Next step, the membrane edges. The membrane edges, they come from my links. So here they are. I would reference them again using telepathy. So these are the geometrical elements. We can group these and put them down here. And then I want to copy past these. No, this one. And I want to reference cable edges. We want to make cable edges. And I have a cable 16, that's element number 1. And then I use telepathy, and this is my cable. So we have referenced the cable seed. This is the material clearly. And so we have the cable seed. To generate the cable edges, we go into Xcube, and we have link set. The link set wants the seed. Here it is. Then it wants deformability. Remember, deformability means if the edges deforms with the membrane when we want the form finder or no. In this case, the boundary edges are cable edges, and we want them to follow the membrane, so they are form find deformable. The type of element, we can have cable, truss, or beam. Clearly, these are cable elements. And then we have the geometry and or the edges. What is missing here is the pretension. The Q is the pretension if we are using the natural first density method. It will be the first density value if we are using the first density method. We will input a value of 10. That will be the pre-stress of these cables, the initial pre-stress of the cables. So I will group these together. Again. Then I will send you this definition. That's why I'm making it a bit more ordered. These are cable edges. Okay. Let's turn this down here. So we have made the membrane and we have made the edges. What is missing? We need to input the links. The links is quite simple. It's this one here. So we can reference the geometry and call it links.
Jerry, I think
Yes.
there's a mistake, a copy-paste mistake from earlier. You can see.
Yes. The links, here we are. Generally, a nice thing is I put even here. This is my BREP. I hate all these spaghetti elements. That's why Grasshopper let us make a nice, clean definition. So I get the links here. For the links, we have something very similar to the cable edges. I will do a copy paste. Clearly, for the geometry, we input the links and we take off the edges. Cable 16 can be okay. It's cable, takes 16, form fine deformable. So this is okay. These are the links. Okay. What is missing here? The cables. These are the stay cables. So we reference the stay cables, and then we have the poles, and these are the poles. So we reference the poles, double click and double click to get these out. I will copy and paste this. The poles go here. These are beam elements. We are making the poles. We have to change the definition, and these are stiff deformable. We need the seed, so I get a new seed here. And we will use what we have here. We need another cross section. So I will show you now how to add a new cross section running this definition. If we go here into Xcube, we go into the post-processing tool. We have this icon called code or checker, but this one recalls a number of panels from Xcube. The one that we want to recall is the profile manager. And we can bring up the profile manager from here. So I just want to input a pole, 193 diameter is okay. So I add it to my model. I close with OK. And now if I go into the seals and I say update, I have a new pole here. So element number 9 is my pole. There's one thing to say. You must be careful. If you want to start this definition again later, and later means tomorrow or another day, what will happen that if I load the default template from Xcube, I will not find element number 9 because the first 8 elements were inside the template that we have used. But if I start again later and I start from the default template, clearly the profile number 9 will not be available. Now, this is only one, but think that you have added and changed a lot of these profiles, your definition will not work anymore. How can we avoid all this? Well, we can go into Xcube. Clearly, we can go to here, and for example, I will add more of these profiles just to show you the difference. All the elements that I want to use, materials and whatever it is. Now, what can we do? I can save this as a template. So save as template. I give it a name, Grasshopper, for Grasshopper. Okay. We have saved the template. If I turn back to Grasshopper now, and I start from here, I go into an empty space. We go into the Xcube global. We have here an option called templates. If you update, it gives you the list of available templates. Okay. And clearly, what we would like to do is to start always from the same template. So the template that we want to use is the number 7 for Grasshopper. And if we go back to Xcube into the global section, we have two options. The first one is open file. And the second one is save a file. What we want to do, I want to open file template number 7. So I use the list item, the file name of template number 7. So this is the file name of my template, and I want to open it. Then what I want to do, as soon as I open the template, I want to save it. So I connect the open event with the save, and I want to input my also this is a iPad Jack EXF. So as soon as I open the template, I want to save the file into C Alto iParjaka EXF. When you do this, you must be sure that the folder exists. So let's go to the I will check that this one exists. I am making a new folder just to show you. I will make a new folder here. I don't have Alto, so I make a new folder and call it Alto. If the folder does not exist, it will not be able to create this one. So doing this, as soon as I click on run here, if we go back to Xcube, you see that the name of the file is C Alto iParGH. Going back to Grasshopper, if I update my seed list, you see now that the seeds are all the seeds that we have defined in the template are available. And that means that when we start using this template like this, we know that we always start from the same position. Okay. So later, if you have to run this template, this Grasshopper script in a few months, using this initial template definition, everything will work nicely. If you don't do this, maybe it gets broken because something will be missing later. Okay. Fine. So what I want to do now, let's go ahead. I want to reference 193 poll, and this is my poll. And let's reference it again. And this is my poll, 193. It's always a good idea to write the name here, for the simple reason that if you start again after 6 months, you're able to understand what you have done. And the seed, this is sorry, this is my links. No, these are my polls. And stiff deformable, clearly the priestess doesn't really mean anything. So you see, for beam elements, we just have to input the geometry, the type of element, it's a beam, the seed, that's the pole, and the deformability. We can have also the releases, the end releases of the poles. And in this case, maybe we have to input the end releases. If we look at the geometry, what do we want? For the poles, we would like the poles to be pinned on the ground. If we look at the orientation of this element, annelids direction, we see that the poles go from bottom to top. Again, looking at this one, it goes from bottom. That means that the bottom point is point A and the top point is point B. And if we go into the reference here for the poles, we see that we have A release and B release. Where do we get these releases? If we go back to AX3 get, we can get the DOF releases. What is the DOF releases? We input this in a panel so I can show you. This is a table of end beam releases. This is the connection between the beam element and the node. Okay, so any beam element has two nodes. The first node, node A, and the end node, node B. The connection between the beam and the node, there are 6 degrees of freedom. So there are 6 connections. And remember that the axis of the beam is the x-axis. I think you remember this from the past. The x-axis is the axis of the beam. And then we have the y and the z-axis, or the axis in the plane, the cross-section of the beam. So basically, what do we want? We want them to be pinned on the bottom. So pinned YZ is the release that we want. This means that the beam will be able to rotate around the local Y and the local Z axis for the first node. So we can reference this list item number 3. Here it is. And we use again telepathy, and this is release YZ. We get release YZ and we input into the A release. Okay. If we want to see where these objects are inside AX3, if I turn back to the software and we go into tables, beam DOFs, here they are. So if I click on pinned YZ, you can see here that pinned YZ is the rotation around the local Y axis is free, and the rotation around the local Z axis is free. All the other constraints are fixed. All the other DOFs are fixed. And here you can see these images. What does that mean? X, it moves in the local X direction. Y, it moves on the lateral side. Z on the other lateral side. And then we have 3 rotations. Okay. Let's turn back to the grasshopper. I will get this. I will group it and move it a little bit away. So, what's missing? Stay cables. I'll get this. Control C, Control V. These will be my stay cables. And clearly, the curves will input the curve elements. These are cable elements. They are stiff deformable. And then, not pole, we have to input. We don't need releases for the cables. We need the seed, and we can use the cable 16. So cable 16 will be the seed. What we need to input now is just the pretension of the cables. This is the initial pretension. Since these are stay cables, we do not really know which will be the final pretension, but this will be available after the form finding. The amount of pretension in those stay cables will be available after running the form finding. For the moment, I will just input 10 kilonewtons. It's a guess more than an input. So this is my initial pretension for the stay cables. Okay. These are the state cables. Okay. Let's move it up here. There's one thing that is missing. You remember that when we do the form finding and the structure analysis, we have to define, we select the nodes and we define the restraint of the node. Clearly, here we don't have access to the nodes because they do not exist in this moment. Until we generate the model, the nodes do not exist. So how can we solve this? Well, easily, we have made this points. That's a list of points. We use again, these are my nodes. We reference this geometry. If we go back to Xcube, we have a node set. A node set, simply we define a number of constrained points. We need to input a list of points, and then we need to input the restraint. We have a restraint definition here. And it's quite easy we want them to be all fixed. So this is just a node set. Everything is clear up to this moment. I think yes, no? Quite simple. These are the restraints. Fine. We have basically defined everything. Now we just have to generate the model. So this is the easy part. First thing, we want to generate the membrane. For generating the membrane, we need to generate a tensor group. So here's the tensor group definition. You see that the only input is a mesh set, and this is my mesh set. What are these two here? Well, the first one is the name of the group, and this is my membrane. This would be the name of the group generated. And this is the layer inside which we will generate it. I will call this again membrane. To generate this this group, we can click here on the update button, or we can input a bake Boolean flag here. So what I will do is very easy. I will make a button. Where is it? And this is my baker. You remember my baker, the song. This is my baker. I will plug in the baker to telepathy. And then I will plug it here. So when I run this, when I click on this baker, all these groups will be generated one by one. The cable edges. The cable edges are cables. So we go into Xcube, and they will belong to a FEM2D group. A FEM2D group, if you remember, it's a group that collects two-dimensional elements. The name, these are edge cables, edges. And I will put them in the membrane layer. Like that. And he just wants a link set. So here it is. And I will get the baker. That's it. The links. The links again are two-dimensional elements, and we need to create a FEM2D group. These are my links. And I will put them again in the membrane. There's one thing that I would like to do, but I'm not going to do it in this moment. It's a bit more tricky. The links, we have to set a constraint on the links. And in this moment, it's a bit tricky to do it. So I will skip this. I will do it later in the Xcube interface, setting the fixed length for the links. Let's get the Baker. That's it. The poles, I can get this copy paste. The poles again is a link set. The name is poles, and I will put them in the steel layer. Then we have the stay cables. I will leave them in the steel layer. And then the last one are the points. For the points, there is a special group called node group. A node group is a special group because it's an empty group. There's no geometry inside the node group. And I will put them in the layer nodes. You see that the node group wants a node set, and it wants a restraint. Let's get the Baker. That's it. I think we have done everything. We can save this. Basically, to run the script, we just click on this one here. This one will start. We could even link it to. This is my run button, but I can link it to my Bakeit. So when I start from here, what happens? We open the template, we save the name, the file, and then we run the definition. Let's see what happens. So if I have not made mistake, it's running Xcube here. Here we are. So basically we see we have the mesh, but the mesh, you see, it's upside down. The positive side is on the bottom, and it's on the top, and the negative side is on the bottom. If we unhide the nodes, let's try to. We see here with that we have these nodes here that they are fixed, and these belong to the node group. If I select this stake edge cable, we see that it's a cable, it's non-linear, it's stiff deformable, and so on. So if I have did everything correctly, one thing that I want to fix, if I go back here into the mesh set, you see that we have a Boolean flag here, flip. And yes, I want to flip it. So I input a Boolean toggle and I set it to true. If we turn back in Grasshopper and I click again on this one, when you click on this, everything starts from scratch. Oh, now he's running the software now. Yeah, so now you see that everything is in the correct. So basically, we have generated the geometry, the membrane, the edge membrane, the edge of the membranes, and everything in one shot. There's one thing that I need to set. The links, these have a constraint. They have a fixed edge constraint. So we need to set here, we need to set on fixed current length. And if everything is has been done correctly, we can try to run the form finder. Let's make 20 loops because we have a nonlinear form finder. And let's try. Yeah, that's it. So basically, we have run the form finding. We can give a look at the reaction forces. You see the reaction forces. You remember that I have set 10 kilonewtons for the stay cables, the initial pretension, but at the end, the initial pretension is 15.6 kilonewtons. This equilibrium force is the initial pretension. If we look at the membrane precess, we see that we have 0.8 and 0.5. Why we have a different value from the initial 1 kilonewton per meter? We have an initial deformation of these poles. If we look at the deformed shape, we see that this pole has moved 4 millimeters. So the initial precess, the form finding precess was 1 kilonewton per meter. But since the pole has relaxed, the membrane has lost an amount of precess. So basically, here you need to loop a little bit. So maybe we can start with a higher precess, or we have to make these cables a bit more stiff. The initial pretension should be a bit more higher to avoid that it moves too much, and so on. Okay. So we are ready to go to the next step. The next step is to run the analysis over this membrane. How do we do this? First of all, we need to apply the loads, wind loads, snow loads, and whatever loads we need. To do this, we right-click on the loads, load manager. The first load that you will generate is the self-weight. You just have to generate a self-weight load and nothing else. The software will fill it with the self-weight of the objects. So the only thing that we have to do. We want to generate wind loads. Now, if you remember, we have discussed about the wind loads. Wind loads need a little bit work because we have to calculate the CP values and the pressure and all that stuff there. So I will skip this. This is your part of the job. I will show you once we have done that. I mean, we have on paper everything already written down, the amount of the CP values and the areas where the wind blows and so on. We can apply the loads on the surface. To do this, I am going to activate only the mesh filter, so I can select only mesh objects, and I'm going to use the select by polyline, and I will select something like this. I am using the C key to close the polyline. So I have selected this part of the membrane. And I'm going to save selection like S selection SA. Click on save, and that's it. I'm going to do the same now for B. So using the polyline tool. I have selected this part, and I'm going to save this area as SB. Save. What we want to do now, well, into the scripts, we have these nice wind load tools. So I am going to recall the Eurocode wind load. The Eurocode wind load is asking for the wind speed, 33 meters per second, the zone, the terrain category, and we are going to use urban area. And then the input parameter, we need to input the topographic factor, CT. You'll find on the Eurocodes what this number is and how to compute it. But let's say that generally you don't find much information, and 1 is the input. The CD is the dynamic factor. And then we come to the most important factor, that's the CP value. The CP value depends on the geometry and on the geometry basically. And since we are going to generate a load that blows in this direction, so we have a pressure on the first part and a suction on the second part. A positive value means pressure, and the negative means suction. So our input 0.8, and the selection zone is SA, and I want to generate wind X. So you say generate pressure loads. You see that he loads the selection and computes the wind pressure, and he applies the wind pressure on this area. We want to generate the pressure on the other side, but this is a negative pressure, it's a suction, minus 0.6. I want to input in the same load case, but we want to use selection B. So on the B area, we want to have negative pressure. Generate pressure results, and you see here, he is computing that. If we want to check these values, we can go into options, wind, and we can see here that we have the red is a 0.85 pressure, and the blue is minus 0.63. Okay, so this is a wind load. Let's save. Clearly, in this example, I am generating one wind load, but for a real world example, we should generate wind load from this side, then at 0 degrees, at 45 degrees, and so on. For a symmetric model, maybe you can generate less, but for generally tensiles are not symmetric, so, or any geometry that is not symmetric, we need to generate more wind load conditions to capture the behavior under different actions of the load, of the input load. Let's go ahead. Yes.
One quick question. Usually you have some uplift in the flat areas. Is it transformed into uplift by the geometry, or do you have to input it as a different load case for wind?
No, the uplift comes in automatic. If I look at this wind load here, and we print loads, you see that we have, this is the overall pressure on the surface. This is the overall vector here. You see that the overall vector is in the X direction 4.9 kilonewton, in the Y minus 4, and in the Z direction minus 2.56. It means that it's suction. It's pulling the surface. So the suction comes in automatic depending on the geometry. Since we are using the pressure is a value that acts normal to the surface. So when we apply a negative pressure, it's becoming a suction on the surface. It's pulling the surface upwards. Okay. So these are all the loads when we are doing the wind load, depending on the CP values. This is generally a positive CP value will push on the surface. A negative CP value generally is a suction, will pull the surface. So all the different CP values that we evaluate will generate these suctions, pressure and suctions. And clearly, on the norms, we'll find out if the surface is open so the wind can go inside, we will have two CP values, CPE and CPE, the external and the internal wind pressure. And generally, we have to sum them to get the overall pressure on the surface. Okay, so we can say.
Sorry, just for understanding, to make it clear, because you named it wind X. So the value that you input, is it kind of split into from the horizon? Is it kind of like the input a horizontal wind load that is split and or transformed to make it kind of like adapted to the geometry, or is it directly applied to the geometry?
This is
the value.
The value is the CP value. What makes the difference is my selection. I mean, I have selected this. It's not really a wind X. It's yeah, the name is not really correct. This should be wind minus 45 degrees should be the name. Basically, in my mind, where is the drawing here? Yeah. Basically, I was thinking about this input here. So this is my wind direction. And if you use this as your wind direction and you compute the selection area and the CP values, or the only input that we have used. So basically, you do this on paper. What does that mean? When we compute this is my drawing, and then you define the wind input. Okay. Now, based it on how, so one of these arrows can be the wind input that we define. Once we have defined the input of the wind, I'm a bit slow in selecting these. Once we have defined the input of the wind, in this case, this input, for example, if I go UCS vertical 2 points, this will be my geometry. This black line here. So this is the section, no? The section of the geometry in the direction of the wind. Based it on the cross section, we go into the Eurocodes or into the codes that we are using, and we evaluate the pressure, the CP values, and the pressure based it on the geometry. Clearly, if the geometry is complex, maybe we have to make more than one slice. Based on these slices, we are able to evaluate the behavior of the wind in this direction. So we are thinking, looking from top, that the wind is coming in this direction. The wind is blowing in this direction. And which is the behavior based on this curve? It will have a pressure, an initial pressure in the beginning, and then it will become suction on the other side. And on paper, we make these zones, the one that I have selected in red and in blue, we draw them on paper and we compute the CP values in those areas. Okay, so at the end we have, for the wind at minus 45 degrees, we have all these zoning areas with this CP value. positive or negative CP values. Once we have done all this work, we come here, we select the areas, the zoning, A, B, C, whatever it is, and we input the values in this tool here to generate the pressure on the surface. So basically, the pressure on the surface, in this case, depends on the selection that I have made and on the CP values that we are using. Clearly, the height of the structure is evaluated in this formula, but that's what is important is the CP value. Is that clear? It's a bit tricky, clearly, but that's the only way we have at the moment to do it. So once we have done all these nice wind computations, clearly, if we want to evaluate snow load, for example, we can go here and we can ask to plot the slope. This is the slope of the surface. You see that we have blue is almost 0 degrees, 6 degrees, and so on. So this is the angle. The slope is the angle between the face and the horizontal plane. For example, when it comes to apply the snow load, some norms say that if the slope is more than 30, 40 degrees, we do not apply for the snow load. But in this case, it doesn't happen. So if I need to apply a snow load on this one, we go into the loads. Load manager, new load, snow load, and I call it snow. To apply the snow load, it's quite easy. I just need to select the membrane. You right click on the snow load, load selected. The snow load is not a pressure load, it's a gravity load. So it acts on a projection on the ground. And here we just input the positive value, that's the amount of gravity load, 0.5 kilonewtons per square meter, and you click on apply. So here, if we go into the plots and we look at the snow load, we see that we have applied 0.4 kilonewtons vertical load. Okay, let's take off this slope color. Now it's time to run the analysis. We make different load scenarios and rename these to ELS. The self weight 1.4, and then the wind load here 1.5, the snow load 1.5, and then maybe here 1.4, 0.9. So these are the load scenarios. Clearly, since we are running a nonlinear analysis, these have to be run one by one. And here we have the input. When we are running a highly nonlinear problem, it's good to start with at least 25, 35 increments. You remember the increments is the nonlinear. We split the load in 35 steps, and the iterations is let's put 50. Here you can put how many you want. He will use the amount of increments needed and will skip. And run the analysis, and let's see if it converges. Generally, if your model is nicely designed and is stiff from a geometrical point of view, you will not face big problems in running the analysis. Okay, so we have run all the analysis. Now we can go into the response. And for example, for load case number 2, the wind load, we want to see the deformed shape. And clearly it's clear the loads that we have input here. Now we have made pressure and suction. F3 will show you this animated deformation. If you want to query and have information about the model, you can open the post-process view. And as soon as you select elements, the post-process view will give you the information about the elements. In this case, the membrane is giving us the warp and the weft precess. If I select the pole here, my filter. If I select the pole here, it will give me the information of the pole. The pole has minus 150 kilonewton compression, and selecting the cables are 63 kilonewton, and so on. If we want to look at the envelopes, options, take off the load mode, envelope results, take off these. What is the blue here? I don't want. I want to look at the envelope membrane stresses. Okay, so we choose the stresses that we want to show. We choose the envelope results. So the envelope results basically will envelope all the stresses for all the load conditions, and we plot the maximum values. The maximum values for the membrane. For the beams and cables, we'll plot the negative minimum and positive maximum. For the membrane, since the membrane has no negative values, he will plot from 0 to the maximum stresses. So here we see on the membrane that we have a maximum stress of, the green area is about 7-8 kilonewtons per meter. If we want to check the membrane, remember that we have here load cases. We have made 4 load cases, and we want to check the membrane. We can go into the scripts, into the post-processing, and we can recall the membrane design tool. The membrane design tool has been designed to check the membrane. We open the property panel. In the property panel, we have the membrane design option. In the membrane design option, we have 3 methods for checking the membrane. The A factors, this is an old method, the American Standard method, and then we have the Eurocode draft method. So this is the one that we want to use. How do we use it? You make a kappa set. It has a default kappa set. What is a kappa set? It's a list of numbers of these K values, and basically they define a safety factor. The safety factor here, we see a row based on the number of layers on the membrane. So for the safety factor, we can see that the final safety factor here is 4.36. But if the membrane has more than 1 layer, for 2 layers, it would be 1.9 multiplied for 36. For 2 layers, 2.6, and so on. What does this mean? If we have 2 layers of membrane, the strength of 2 layers of membrane is not equal to 2, but it's equal 1.9 times the value. If we have 3 layers, it's not 3, it's 2.6. So clearly, we say that 2 layers of membrane don't have the strength of 2 layers of membrane, but it's a bit less for a safety reason. So once we have defined this, we right-click on the model, we apply design settings that we want to use, and then we double-click to check the membrane stresses. We see a green line, and that means that the safety factor is okay. We have a safety factor in the warp of 1.19 and the safety factor in the weft of 1.11. And here we can see all the calculations that he has made to check that the membrane is within the safety region. If we want to check the steel and the cables, we enter the Eurocode panel. And here we need to apply again a design setting rule. And for example, we click on the poles. He loads the 2 poles. And here we click on this tool here that's check the elements. The software, we go through all the load cases. And we see that if you see a green line, it means that it has been verified. In this case, the safety factor is 3.93 for one of them and 3.90 for the other one. And you can see where does the maximum safety factor come from. Is telling us that the 3.93 comes from the backlink check. And we can see it here, there it is. 3.93 is the backlink check. Now, and then it gives you here the overall information about how clearly more than one check is done. Generally, we do a check for the strength of the element, a check of the backlink of the element, and then if torsional factors are available, it will check also the torsion, the local torsion and backlink of the frame. Let's check the stay cables. Again, clearly the stay cables, no backlink. Only the strength is checked for the stay cables. And we can see that the safety factor, well, in this case, cable number 2 has a safety factor of 1.5 here. And means that these are the cables that we have to use, 16mm cable. Okay. Yeah, and that's it. I mean, for running and checking the analysis, this is the rule. Let's make a break, 10-minute break. I need to get a coffee because he didn't get coffee yet. And then we will do patterning. Okay. Is that okay?
Yes, perfect. Thank you.
Okay.
So 10 minutes break?
10 minutes break.
Okay.
Hello?
Yes, Trevor.
We are ready?
Yep.
Okay, let's go to the final step. The final step is producing patterning and production objects. So once we have done all the nice analysis and design, we can click here on the right tool. There is a pattern tab. Clicking on the pattern tab, we enter the patterning layout. Once you do this, we see only the edges of the membrane. Now, if you do not see the edges of the membrane, it means that the mesh is wrong. There's something wrong with the mesh. So we have to go back and we have to check the mesh. The mesh could be that it has wrong faces or overlapping triangles or something like that. So we need to use Rhino, AutoCAD, or there is a tool inside the modeler. There is a tool called under the mesh, call it validate mesh. It will check and delete any triangle meshes that are not correct. So this is one thing to say. Generally speaking, if you have generated the mesh inside Xcube or inside the Grasshopper with the 3 mesh and so on, generally it should work. If it doesn't work, we always can remesh it using the remesh tool. And generally the remesh tool will fix any issues with the mesh. So, okay, that said, we can go back here. What does patterning mean? Well, first of all, we must understand that we have, generally speaking, we have a double negative curvature surface. In each point of the surface has a double negative curvature. That's a local saddle shape in all the points of the surface. Now, if we check what does a developable surface mean, mathematically speaking, a developable surface is a surface that has at least a constant Gaussian curvature in one direction. And this mathematical definition for a developable surface never matches a tensile structure surface. So this means that we have to cut the surface, but even cutting the surface, the local surfaces that we generate are non-developable. And then we have to flatten these pieces of surface on the ground. So when we do this, we always make mistakes. There's no exact solution to flattening a double curved surface. Anyway, how do we go ahead? Well, first of all, we need to define, we select the group that we want to cut. The first thing that we do is we cut the surface. Cutting the surface means we have different cutting tools here. The most simplest one is single cutter. A single cutter shows this line here, and we can click on the endpoint and move the line like this. And clearly we can snap to only to the edges of the boundary. See how I move it? When I move it, oh, the line moves on the edges of the boundary. So we place it where we want to place a cut. This is the line. And then you see on the toolbar, we have different options. The first option is section, yes or no. What is that? If we choose section yes, then practically you see that the color changes from green to red. Section no, it becomes green. Section yes, it becomes red. Making a section, well, it's something quite simple. You can think that through this line, a vertical plane passes through that line and will cut the surface in two pieces. If I say make it, you see that he has generated this curve here, this gray curve. The gray curve is the intersection between the plane and the surface. Ask to delete the comment. Now, why we would like to use a cross section, a section? We use sections when we want to make symmetrical patterning. But generally speaking, we never use sections for a simple reason that a section, when we flatten on the ground a section curve, the section curve tends to become a banana-shaped curve. So I just want to remove this section curve. We can find under the patches, under the section here, this is the list of the curves. We have the section tool. You can right click and delete it. Let's recall again the single cutter. I do not want to generate a section curve. So when the section option is set to no, we are going to generate a geodesic curve. So if I click again on make it, well, we see that nothing really has changed for the simple reason that in the middle of this line, a section and a geodesic are exactly the same thing. But what is a geodesic curve? Well, you could think a geodesic curve to be a line on a curved surface. So it has different properties. The first property is the shortest path between 2 points, but we are not really interested in that. The most interesting property of a geodesic curve is the fact that it is a line on a curved surface. And that means basically that when we flatten on the ground a surface, a part of the surface defined by geodesic curves, these tend to be straight edges. So you understand that when we want to develop and when we want to produce flattened parts of surface, we want them to be the most straight as possible because we have to cut these membranes out of a roll of membrane that has a fixed width. Let's go ahead. We can move this like that and make another cut. So I can move it like this. I am clicking on the M key. You see here, M is make it. And each time I click on the M key, it generates a new cut. M key, M key, M key, and so on. So escape. So I have generated these crazy curves. These are geodesic curves. And you see, as soon as I click on one of them, we can still select the endpoint of the curve and move it, and he will move the geodesic to another place. Like that. So these will be my cutting curves. We are going to slice the surface over these curves. The part of the surface between two consecutive curves and the boundary edges, we call it a patch. It's a piece of surface, and the patches will be flattened on the ground into patterns. Okay, so this is the process. It's quite simple. We generate cutting curves. the boundary of the cutting curves become three-dimensional patches, and each patch is developed, smashed on the ground into a pattern. We have any freedom to define whatever we want. I made a mistake there. We can move it like that and make cross intersection curves. So you can generate any kind of strange patches that you want.
Sorry, Gary, I have a question here. Could I ask? It's that you use a section curve to cut the surface, or is cut the boundary? I mean, and the curve that we cut at the section line is have the curve which follow the shape of the surface, but I think I was thinking, did you like select the surface of the membrane, or you just select the boundary? If you just select the boundary, how it make it follow the
No. We see only the boundary, but the surface is hidden.
Oh, okay, yeah.
The surface, he knows the surface. He's showing me only the boundary to avoid confusion, but he knows that he has the surface under. I don't see it, but he's following the surface.
So that like all the curves that they show is exactly on the surface, right?
Exactly. Yeah, you see that they're on the surface. He's generating geodesic or section curves on the surface. To avoid confusion, is showing me only the boundary edges, because I can move only on the boundary edges. I cannot move inside the surface. Okay. We need to make cuts that go from edge to edge.
Yeah. Thank you. Yeah.
You're welcome. I will clear now this mess that I have made. So I will use clear group to clear all these cuts. So I have used the first tool here, that is called single cutter, one cut at a time. The second tool that we have is a multi-cutter. A multi-cutter is like the single cutter. Let's look from top. You have one line. I can move one line like that, but we are generating multiple cuts at the same time, you see. And in the options, we have the distance between the cuts. And for example, I make it 2 meters. And the number of cuts, in this case 16, but I don't really care. In this case, we are generating, you see, we are defining one cut, and he's making a parallel offset of this line. When we recall make it, if we have the option section no, what will happen? The software will make a number of planes, will detect the intersection on the edges, and then we'll generate a geodesic curve. I will click on make, and that's it. He has made all these geodesics. You see that they follow the surface. Okay. This is the second option, multi-cutter. I will clear again the multi-cutter. Another option that we have is the optimal cutter. What does the optimal cutter do? As you can see, the optimal cutter has highlighted 2 edges of my membrane. Generally, we use optimal cutter for panels that have, for tensiles that have 4 edges. He needs 2 main rails. This is one rail, and this is the other rail. He will move automatically the cutter over the rails and find the optimal panels. In the options here, if I slide up a little bit, I have small here. It's okay. Here we have the parameters for the optimal cutter. The desired width, I want the panels to be 1.5 meters each. A tolerance of 5 centimeters. And so we're asking the software, look, move the cutter over these 2 rails, and I want to detect panels that have 1.5 meter width, flattened panels. We click on generate cuttings. He will think a little bit, and then he will make these cuts here. You see that the cuts have an equal distance between each of them. And when we flatten them, the panels that come out will be in the range of would be not bigger than 1.5 meters plus the tolerance, that's 5 centimeters. So this is the other option that we have, the optimal cutter.
So for this shape of the hyper, what cutting pattern would you suggest?
For this, I lost my panel here. For this one here, let me go back. Oh, I'm not able to find this. My screen is too small for doing this. Let me do that. Come on. I lost my browser here. Oh, here it is. Yeah. Let's reset this one. Clearly, we are making an iPad. Remember that when we talked about the stress flow in an iPad, the stresses generally flow from high point to high point, low point to low point. What does this mean? It means that if I have to pattern this, I will use the multi-cutter, and exactly at 45 degrees, the 45-degree direction will be what I'm going to use for patterning this iPad. We want panels to go in this direction for the simple reason that if we are using a membrane with a warp and a weft direction with the warp fibers, I want to layer out my wide fibers in this direction because this is the strong direction of the panels. The second thing, the width of the cuts. The width of the cuts. Now, generally, the membrane that we find on the market has a width that goes from 1.7 to 3 meters. But for a small shape, remember that this shape is 10 meters here, 10 meters by 10 meters. The number of panels that we generate, never make a small amount of panels because the number, remember that when we flatten this on the ground, we are making mistakes. So it's like drawing a circle. Let me draw again to show you this. If I want to draw, this is my surface. And I want to draw a surface using a polyline of points. If you want to draw it only with 3 points, like that, this is your circle here. This is your circle. If I draw a circle using only 3 points, my circle becomes a triangle. So we are making a huge mistake. The curve, this polyline between the circle and the polyline, we are making a huge mistake, this mistake here. So clearly, if the green is your panel, if you make only a few number of panels, since we are making a linearization of the problem when we flatten it on the ground, we cannot make only 2 or 3 panels if we have a high curvature. We need to make more panels. Making more panels means that I make more points like that. And when it comes to make the panels, my panels will be these here. So clearly, the surface that we are going to generate is much more accurate than the previous one. So there is a trend between how many panels I need to generate and how expensive this can be. Remember that more panels we make, more expensive it will be, for the simple reason there's more manual work to cut, weld, and do all that stuff. Okay. So there is a trade between how many panels we need to generate and the size of these panels. Clearly, for a small shape like this, I would not go less than 1.2, 1.3 meters. So here I can set the distance between these 1.4, and we can generate the panels. When the software generates the panels and then flattens them on the ground, there is this angle, deviation angle here. We need to there are 4 master edge points in the panel. In this case, these 4 master points are these 4 points here. We will use them. The software uses these points as control points when flattening it on the ground. This angle here is the deviation angle. We can set it to 160 degrees, 150, 160 degrees. And so basically what we are saying to the software is, look, that when you find that my panel, my pattern has 2 consecutive points, the angle between 3 points is bigger, is smaller than 160 degrees, because generally we will have 180 degrees on the straight edge. It means that I have a corner point there. So keep it and treat my panel as an edge point. Sign it as an edge point. So first of all, make these geodesics, and we have made these geodesic curves. Now I want to generate the panels out of these curves. So we just click on the tool, generate patterns, and you see here, he has generated these patch elements here, and the patch elements have been flattened on the ground into panels. So you don't have to do really so much here. What is important? Remember that we said the 4 edge points. These are the 4 edge points that he has detected. Number 1, generally we have 4 points, but you can have 3 or even 5 points. If this happens, we can fix manually the panel. In this case, he has detected, you see the edges. Generally speaking, we have 4 edges in a panel. We have always 4 edges. We call these the main developing edges. We see them here, green, blue, red, and black. Why do we want to use these edges? Well, they are comfortable for the simple reason that generally we want to check between 2 consecutive edges if they're weldable. I want to know, when we go into the production, I want to see if 2 edges have the same length, because they have to be weldable. If they don't have the same length, I am in a trouble when we go to produce this this overall object. And they have to be very accurate. Let's say that less than 1 millimeter, the length of the welding edges should be not less than 1 millimeter, because I am not able to weld them together if there is a mistake in the length of these. Okay. So basically, we have generated the panels. Remember that these panels, the shape that we have here is a precessed shape. Always keep in mind that your geometry is a precessed geometry. Think it as a rubber surface. So we have this rubber surface, stretch it in the space, and out of this rubber surface, we have generated a piece of membrane, a piece of rubber on the flat ground. One thing I want to show you, since we are talking about cutting the surface, the last tool that we have, if we have used the single cutter, the multi-cutter, the optimal cutter, but we have other features if we need them. And I will make a new layer here, and I will call it CAD. I will activate it. I will enter the CAD tools, activate project on the ground, and I will draw, for example, an ellipsis. No, not like that. I will draw an ellipsis by rectangle, like that. And then I will get this one. I will go into the rotate. Uh, 6 copies. And I will use this point here as the center point. So I have generated these curves here. What I would like to do I would like to use these curves as cutting curves. So how can we do that? Well, a double click on the layer will select these curves. Let's make a new layer. And this layer, I will call it projected curves. We will activate the new layer. In the tools, we have, in the create toolbar, we have the tool project to mesh. Project to mesh will ask me how many projection points, discretization points, 36. I leave it okay. And we have generated curves, those curves projected on the surface like that. So we select these curves. I enter the patterner again. And now we have this last tool that it's called modeler cutting. It means get the selected curves from the modeler and use them as cutting curves. Again, we can use those curves as graphical entities. That means only drawn on the patterns, or as cutting curves. We want them as cutting curves. So I set as graphic curves no. I click to enter, and we get out these curves again. You see that these curves are on the surface. Now, if I generate patterns again, we see now that we have all these pieces of panels on the ground. Now, so clearly, well, this is quite a complex object, but clearly this makes you make any kind of strange patterning. For example, if you want to make different kind of use different membranes, we have made an example with a flower a few years ago where we have used two different white membranes. One was a little white and one was a more grayish element to simulate a flower on the membrane. Just talking about, remember, I was talking about the four edges, the four corner points. Clearly, this membrane here has not four corner points, has 1, 2, 3, 4, 5 edge points. So if we want to change the main developing curves, we see it here. Selecting the patch, we see these corner points, these red dots. We can detect which is the main developing curve by moving these dots like this, for example. So if I move it here, we have these two commands, set seam number 1 and set seam number 2 here. So if I set seam number 1, I am telling the software, look, that this edge that goes here and ends here is the first developing edge. I move these dots over here. I move it over here. I have to take off this snap. Okay. I can move it over here. What's going on? Too small. Let's do it on this one. Okay. I had the projection option activated, so I was not able to move it. So I move these two red dots on one edge of the panel. I set seam number 1. Then I move it to the opposite edge and set seam number 2. So in this case, what happens, if you look at the panel, the black line is the main developing edge, and it goes from this point to this point that I have set here to be the main developing edge, and the same for the opposite edge. I am telling you this because if you see a strange panel flattened on the ground, maybe you have to fix the four control points. Okay, let's go back, reset this, make the panels, and